About 4.5 billion years ago, there was nothing here. No sun, no earth, no moon, no planets, no asteroid belt, none of it. Just a vast, cold, slowly rotating cloud of gas and dust drifting through the Milky Way. Mostly hydrogen and helium left over from the Big Bang, mixed with heavier elements forged inside stars that had already lived and died long before our solar system existed. And this cloud was called a solar nebula. And it had been sitting there relatively undisturbed for an enormously long time, until something happened to disturb it. And the leading theory is that something was a shockwave from a nearby supernova, a massive star that exploded violently and sent a ripple of pressure racing outward through the galaxy. And when that shockwave hit our nebula, it did something crucial. It compressed regions of the cloud. And those compressed regions became gravitationally unstable, meaning gravity finally had enough local density to start pulling things together. And once that process begins, it accelerates, because as matter falls inward, the cloud gets denser. And as it gets denser, gravity gets stronger. And as gravity gets stronger, more matter falls inward faster, a runaway collapse that physicists call gravitational instability, and this is the spark that lit the entire story of our solar system. Now as this cloud collapsed inward, something beautiful happened because of a simple law of physics called conservation of angular momentum, which is the same reason a spinning ice skater spins faster when they pull their arms in. The cloud was rotating very slowly to begin with, almost imperceptibly. But as it collapsed and its material was pulled into a smaller and smaller volume, that rotation sped up dramatically, and instead of collapsing into a perfect sphere, the cloud began to flatten out into a rotating disk. Because material falling in along the equator retained more of that angular momentum, while material falling in from the poles got pulled toward the center more directly, and this disk is called the protoplanetary disk, or sometimes the solar nebula disk. And it is one of the most important structures in our entire cosmic history because everything, every planet, every moon, every asteroid, every comet, formed from the material in this disk. At the very center of this collapsing cloud, where the density and temperature were highest, things got extraordinarily hot because as gas is compressed, it heats up, and at the center the compression was the most extreme, and the temperature climbed and climbed over hundreds of thousands of years, until it reached about 10 million degrees Kelvin. And at that point, something extraordinary happened. Hydrogen nuclei started smashing together with enough energy to overcome their electromagnetic repulsion and fuse, and the first nuclear fusion reactions in our solar system ignited, and a star was born, our sun, which at this early stage is called a protostar. Surrounded by its swirling disk of leftover material, and the birth of the sun released enormous amounts of radiation, and a powerful outflow of particles called the solar wind. And this wind began pushing the lighter gases, hydrogen and helium, away from the inner regions of the disk, and out toward the outer regions, which is why the inner solar system ended up rocky and the outer solar system ended up made of gas and ice. A boundary that planetary scientists call the frost line or snow line, sitting roughly where the asteroid belt is today. Inside the frost line, in the hot inner disk, where the sun's radiation was strongest, only rocky and metallic materials could survive: silicates, iron, nickel. The building blocks of what would become Mercury, Venus, Earth, and Mars. And these materials began to stick together through a process called accretion, which started incredibly small with dust grains colliding and sticking to each other through electrostatic forces. The same kind of static cling that makes a balloon stick to a wall. And these dust grains grew into pebbles, and pebbles collided to form cobble-sized rocks, and those collided to form boulders. And eventually, the boulders grew large enough that their own gravity started helping them accumulate more material. And at this stage, they are called planetesimals, the building blocks of planets, and the inner solar system was absolutely packed with them. Billions of small rocky bodies all orbiting the young sun and constantly colliding with each other in a chaotic, violent dance that would last for tens of millions of years. The largest planetesimals grew fastest because stronger gravity means you can sweep up more material. And as they grew, they carved out orbital zones around the sun, and eventually 4 dominant bodies emerged in the inner solar system: Proto-Mercury, Proto-Venus, Proto-Earth, and Proto-Mars, though they were still being bombarded constantly and their surfaces were completely molten. Global magma oceans driven by the constant impacts and by the decay of radioactive elements that had been baked into them during formation, and this period is called the Hadean Eon on Earth, named after Hades, because conditions were genuinely hellish by any measure. Meanwhile, out beyond the frost line, where water, methane, and ammonia could exist as solid ice, the building blocks were both more plentiful and different in character. There was far more material available out here because ices are so common. And planetesimals formed just as they did in the inner solar system, but on a much larger scale, and eventually 2 cores grew massive enough to do something the rocky planets never managed, which is to reach a critical mass, believed to be roughly 10 to 15 times the mass of Earth, beyond which gravity becomes strong enough to pull in hydrogen and helium gas directly from the surrounding disk. And when that threshold is crossed, the planet enters a runaway gas accretion phase where it grows incredibly rapidly, ballooning outward in mass in just a few million years. And these two planets became Jupiter and Saturn, the giants of our solar system. With Jupiter becoming the largest at over 300 times the mass of Earth and Saturn growing to nearly 100 times Earth's mass with the spectacular ring system that would form much later from captured debris and shattered moons. Jupiter in particular had an enormous influence on the entire solar system because its gravity was so powerful that it disrupted the formation of what might have been a fifth rocky planet between Mars and Jupiter, the region where the asteroid belt sits today, by constantly tugging on the planetesimals in that zone, preventing them from accumulating into a planet, stirring them into elliptical orbits where collisions became too violent for accretion to win. And so instead of a planet, we got the asteroid belt, a collection of leftover rocky debris that adds up to less than 4% of the mass of the Moon, a graveyard of planetary building blocks frozen in time. Out beyond Saturn, where the solar wind and radiation were weaker and ices were even more abundant. Two more giant planets formed, Uranus and Neptune, though they followed a slightly different path, accumulating large icy cores, but not quite reaching Jupiter's runaway gas accretion threshold before the disk began to dissipate, ending up as what scientists call ice giants rather than gas giants, with compositions dominated by water, ammonia, and methane in exotic high-pressure states. And both of them ended up with their own collections of moons and rings, and Uranus famously ended up rotating on its side. Almost certainly the result of a massive collision with an Earth-sized body during the chaotic early period of the solar system, about 30 to 50 million years after the Sun formed. Something dramatic happened to the outer solar system in an event that scientists call the Late Heavy Bombardment, or sometimes the Grand Tack hypothesis. The leading model suggests that Jupiter actually migrated inward toward the Sun early in the solar system's history, pulled by interactions with the disk of gas and dust. And as it moved inward, it disrupted the asteroid belt and the outer planetesimal populations, scattering debris across the entire solar system. And then Saturn's gravity eventually pulled Jupiter back outward. And as the two giants swept through the solar system, they sent enormous numbers of comets and asteroids raining down on the inner planets, and the Moon bears witness to this bombardment in its ancient cratered highlands. Craters that were formed during this period of intense impacts that scarred every solid surface in the inner solar system. The Moon itself formed from one of the most spectacular events in Earth's history, called the Giant Impact or the Theia hypothesis. Roughly 45 million years after Earth formed, a Mars-sized body that had been growing quietly in a similar orbit collided with the proto-Earth in an oblique glancing blow at tremendous speed. And the impact was so energetic that it vaporized a huge portion of both bodies, flinging an enormous cloud of molten rock and vapor into orbit around what remained of Earth. And this debris cloud quickly coalesced under its own gravity into the Moon, which at that time was much closer to Earth and appeared enormous in the sky. And over billions of years, tidal forces have gradually pushed the Moon farther away, and it continues to recede from Earth at about 3.8 centimeters per year to this day. About 4 billion years ago, the solar system began to settle into something approaching its current configuration. The Sun had blown away the remaining gas and dust of the protoplanetary disk with its solar wind. The planets had swept up or ejected most of the leftover planetesimals. The orbits had stabilized into the nearly circular coplanar arrangement we see today, and life, at least on Earth, was just beginning its first tentative experiments with chemistry in the warm, shallow oceans, fed partly by organic molecules delivered by comets and asteroids during those final bombardment phases. And the 4.5 billion years that followed would bring the full sweep of geological history, the rise of complex life, the emergence of intelligence, and eventually a species that would look up at the very solar system that formed them and begin slowly and painstakingly to figure out how the whole thing started.